All right, so, well, just before we really get started, as John said, feel free to jump in with anything, from your own experience or questions as I go along. Paul and some of the other bridge guys, if you have a comment from kind of your perspective, jump in and feel free to comment. So this presentation here is just kind of a general overview of drilled shafts, mainly focused on the construction process and kind of focused on larger shafts constructed in a marine environment, kind of focused on what we expect to see at Red Wing. So first, I'll go through a little bit of background from kind of a designer's perspective and how drilled shafts function as foundations. And then we'll go into construction, the different methods, and then look at kind of pieces of the methods, pieces of equipment, and that kind of thing. So any kind of foundation, its basic function is to resist the loads from the structure. And so those loads can either be vertical loads, which are pretty much weights, weights from the structure or weights from stuff on the structure. And then lateral loads, which are basically forces acting on the structure, like wind or water or earthquake loads, that kind of thing. Usually there's one major lateral load that's kind of driving your design. So for example, at Red Wing, we're on the Mississippi River, and vessel collision is kind of driving our lateral foundation design. So vertical or axial load on a shaft is resisted by two components. The side resistance, or essentially the friction along the side of the shaft, and then base resistance, or just the bearing of the base of the shaft on whatever material it's bearing in. So this is a plot of some resistances versus displacement. So first thing to note is that to develop vertical resistance or axial resistance, there has to be displacement to develop it in the geomaterial. So if we were to perform an axial load test on a drilled shaft, so we build a shaft and then we push on it, and we measured the top displacement, we would get this top curve you see here, the thicker black line at the top. And then if we broke that down into components of side or base resistance, we would see that the side resistance develops at much smaller displacements. And it hits some peak value and then generally kind of levels off. This plot shows it decreasing a little bit after it peaks. It may do that depending on the material. It may increase a little bit, but basically once it hits its peak at a pretty small displacement, it's pretty constant in terms of side resistance. Base resistance, on the other hand, takes much larger displacement to develop. And so the key takeaways from this slide are, one, that side and base resistance develop at different displacements. Also, we give the shaft a number that we call its nominal resistance or nominal capacity, but that's not a real well-defined point on this curve. You have to use some engineering judgment to select, what is the axial resistance of this shaft, and that kind of depends on what is a tolerable displacement and what kind of material you're in. So just kind of recapping, like I said, side and base resistance develop as a function of displacement, and they develop at different magnitudes of displacement. So side resistance, we generally say it develops about a ½ inch of displacement. Peak side resistance, like I said, once you reach the peak, it's kind of levels off after that and doesn't really decline substantially, if at all. the displacement to mobilize base resistance is larger. It's generally kind of a function of how big the shaft is. So depending on the material, we'll say it's about 4% for shafts in rock or cohesive soil like clay, or about 10% for sands. So as you can see, if you've got like an 8-foot shaft in sand, the displacement to mobilize the side resistance is only like a ½ inch, but it's like 10 inches to fully mobilize the base resistance. And for axial resistance, the structural properties of the shaft, in other words, like the strength of the concrete, the amount of reinforcement in it, don't really have a big influence on this axial load transfer. It's just acting as kind of a rigid element, and it's really the geotechnical resistance, the skin friction, and the base resistance that are controlling our axial resistance. So, as we said, construction can have a big influence on the performance of drilled shafts. We want to make sure that we have good, clean sidewalls so that we have a good sidewall bond, because we're going to count on that friction to hold up the shaft and the loads on it. We want to have a clean, sound base, so we want to make sure that we don't have soft material left in the bottom of the hole. We want to make sure that we're bearing in good quality material that we expected to be bearing in. And we also want to make sure that we have good quality concrete throughout the shaft. So lateral load transfer, drilled shafts have to resist lateral loads as well. And we kind of break those down into 3 components: shear, or just horizontal load, moment, or torque, or overturning force at the top, and then axial load plays a little bit of a role in lateral loading as well. So as a foundation, bends over, that axial load, wants to push it over further. That's what we call a P delta effect. The resistance for lateral, it comes from the passive resistance of the geomaterial. So in other words, just the pushing force of the shaft against the soil or the rock, kind of like the picture with the arrows are showing here, as well as the stiffness of the shaft itself. So as I was saying, kind of unlike the axial case where the strength of the material of the shaft doesn't have a big influence, the amount of reinforcement, the strength of the concrete does have an influence on the lateral resistance. So you're having to bend that element itself. So how rigid and stiff that element is also influences the lateral resistance. All right, so we've kind of gotten through the background of from the designer's kind of perspective, and we'll dive into the construction stuff. So the simplest construction method is the dry method, which just means you have a dry hole. And then the other method would be the wet method, meaning that the hole is flooded with drilling fluid or water. With either of these methods, we may or may not use casing to help stabilize the hole as well. And the casing might be temporary or permanent. So just looking at a basic, the most simple case, a dry hole with no casing. We do this when we've got materials that are going to stand open on their own. So it basically needs to be clay, or it could be rock. Certain rocks and soils can be negatively affected if exposed. So we wouldn't want to use the dry method where it would negatively affect the performance of the shaft. The main advantage, or one of the main advantages of the dry method, is that you can visually see what's going on. So that obviously makes things a lot more simple. It's fast and inexpensive, but it's not really our choice as to whether the conditions allow it. I mean, you can't really drill a dry hole out at Red Wing. It would be difficult. Just going through the kind of basic steps in the process. So you just drill the hole, clean it out. You would have some inspection there, making sure the hole is clean, and then place the cage, and then place the concrete. In a dry hole, you can either place it with a tremie or you can free fall it from the top. Just showing, like, if you were combining the dry method with using some casing, maybe you have some superficial sands over a clay layer. So first you install a casing, then drill the hole, clean the hole, place the cage, place the concrete, and then if it was a temporary casing, we'd pull the casing while the concrete's still fluid, and then that fluid concrete will hold the hole open, or if it's a permanent casing, just leave it in place. So the wet method, we can use this either if we're going to have to do it to combat water coming into the excavation from the surrounding material. It can also be used to stabilize a hole without casing. So the key here is we've got a drilling fluid, and so drilling fluid basically just means whatever fluid's in the hole. That might be water, it might be polymer slurry, it might be mineral slurry. If we keep that drilling fluid at a level higher than the groundwater, then we've got a positive pressure in that excavation, which will A, keep the groundwater from flowing into our excavation. And you've got to assume if groundwater is ever flowing into your excavation, you've got to assume it's bringing sediments in with it. And that's a bad thing. Also, it is pushing out on that hole, so it can be used to stabilize the hole. So the big problem is now we can't see what's going on. We're working in the blind, so to speak. And because of that, contractor skill kind of gets upped in terms of their ability and what their experience level and what it takes to build the shaft. And it also is critical that we have good inspection to make sure that the contractor is doing a good job. If a hole is water bearing, you pretty much need to use the wet method, with one exception I'll talk about in just a second. The pictures here are from the Hastings Bridge project, and the contractor was trying to dewater the rock socket. But as you can see, water is coming in way faster than they can keep up with it. And that's, if this is your scenario, you're just way better off doing it in the wet than trying to do anything in the dry. The possible exception here is if you can get a casing down to a non-water bearing layer. So say you've got sand over rock, you can put a casing down and seal it into rock, and then you could potentially dewater your casing and drill your rock socket in the dry. But it's rare that scenario occurs, and you've got to really have a good watertight hole. If water is coming in at any appreciable rate, it's best to just go ahead and flood the hole and construct it in the wet. And even if you could keep it dry enough to drill it in the dry, you've got to make sure that when your concrete is being placed and curing, that you're not having groundwater try to flow in there, which can cause problems with the concrete. So the bottom line is fighting gravity is usually a losing battle. Another scenario is artesian pressure. In other words, the groundwater pressure is enough to where it wants to push water up above the surface or the working level. So this is at the I-35W project, and because there's a dam just upstream, there's artesian ground pressure in the St. Peter sandstone there. And so to combat that, the contractor had to use an extra tall casing and keep a really high fluid level in that casing to counterbalance that pressure that wants to push it up. If they had the casing down at normal working level, water would just be coming out of the casing like that. So looking at the wet method with casing, this is kind of generally what we expect at Red Wing. This is the basic process that was used at St. Croix. Install a casing, either vibrate it in or somehow twist it in. There may be some relief drilling or removal of material in the casing to help facilitate installing the casing, but get the casing kind of seated into the rock. Then excavate and clean, which will all be done under drilling fluid. Place the reinforcement. Once again, this entire process is occurring with a positive head maintained in the casing. And then place the concrete using a trimming from the bottom up, maintaining a positive head in the casing as you place the concrete. So we'll be pumping off drilling fluid or otherwise capturing the drilling fluid as we displace it from the concrete from the bottom up. And then complete the placement. So I should point out the kind of theory in this is that any contaminated concrete or latents and debris rides up on top of that concrete. So whenever we complete a pour in the wet, there's a bit of concrete at the top that we need to somehow get rid of that is contaminated. So you can either, we'll look at it, some pictures in a minute, but there's a couple ways to basically get rid of that poor quality concrete. Here's some pictures of casing at St. Croix. One of the roles of the casing, particularly in marine or over water construction, is we got to have something to form our shaft up in the river there. It stabilizes the overburden soils. It's real critical when you're constructing next to an existing structure, kind of like the Red Wing project, that we don't have a big hole cave in. That obviously would not be good for the piles or the shafts supporting the existing structure. So a casing provides you a good solid way to keep that overburden stabilized. We also want to seat the casing into the rock socket to keep any loose material from the soil over the rock from getting down into the socket. And we want to get a good seal into that rock so that we can not be losing a bunch of drilling fluid into the overburden. And if we were in the scenario where we were going to try to dewater the hole, obviously we would need a good tight, watertight seal. So kind of different ways of advancing a casing. You can just twist it in with a Kelly bar attachment on a drill rig. You can vibrate it in with a vibratory hammer. That's what they did at St. Croix. That's probably, I guess, what I expect at Red Wing. Kind of the most aggressive way It's kind of a specialty way is with a machine called an oscillator or a rotator. You have to use special thick segmental casing with this, and it basically grabs the casing and twists it in, and it can go through very difficult materials. So if, for example, if you have to advance a casing through a hard layer, but then there's a loose layer below that that you need to stabilize, you might use segmental casing for that scenario. Just looking at some different casings and components of them. So like a casing that you might twist into the ground with a Kelly bar attachment, the tip might look like this. So there's a reinforced or a thicker shoe with some cutting teeth on it. This is a tip for use with segmental casing and an oscillator. And then this is a piece of segmental casing. So like I said, that segmental casing has really thick wall, and it has these threaded pin connections. But it's really expensive. Ideally, you don't want to use segmental casing in a permanent application, usually due to cost. For standard, just steel pipe casing, we generally join the pieces with welds done in the field. So just to define some terms and look at the basic components of a standard drill rig. So this is a crane rig. So we've obviously got the crane, and then we have a drill attachment with the power unit, which is pretty much, in this case, just an engine and a transmission. So this is a mechanical type rig. We can also have hydraulic driven rigs. We have the Kelly bar, which is just the bar that does the spinning, transfers the torque to the tool. So the rotary table is just the device that twists that Kelly bar, and then the tool is whatever auger or bucket or tool that we have on the end of the Kelly bar. So now we'll look at some different types of drill rigs. So here's some other crane-mounted rigs. Crane-mounted rigs are what was used at St. Croix. They're commonly used on barges because they have the ability to reach out over the edge of the barge pretty far. Also, they're just using the dead weight of that Kelly bar to put the downforce on the tool. So some hydraulic rigs, you're using hydraulic force to push down on it. And if you do that on just a floating barge, it just rocks the barge and doesn't really work very well. So for floating barge operations, crane rigs are kind of what I expect to see. Truck-mounted rigs, they're pretty simple and obviously easily mobilized to a site, but limited in terms of how big they can be and, application in terms of they can't really reach out very far or reach up over a tall casing or anything. But a lot of shafts put in with truck-mounted rigs. Track-mounted rigs can come in all shapes and sizes. They can be mechanical drive or hydraulic drive. They can be set up for like low overhead situations if you're having to install shafts below an existing bridge deck or something. Looking at the oscillator system, the oscillator is this component right here, which, like I say, that basically just grips the casing and twists it into the ground. To do this, you have to have a real stable working platform because there's a lot of torque that's being applied to that casing. So you have to have a working platform that can resist that torque. And then often the material is excavated with like a grab type tool on the crane when you use an oscillator. Another kind of specialty method is what we call top drive reverse circulation drilling. If you're familiar with like a tunnel boring machine, this is kind of like a small tunnel boring machine on its vertical. It's got a full face cutter, which we'll see some pictures of the cutter in a minute. And it's basically used for rock drilling most often, and it's constantly circulating drilling fluid and cleaning the cutting face as it advances, and it's cutting, like I say, a full face of the rock. Not so common anymore, but manual excavation. This is not allowed in a lot of places, but it is allowed in some places. Some states, particularly in the southeast, it's common for dry holes to send the inspector down the hole. You would only really do that if you've got a cased excavation or a stable rock socket. You wouldn't send somebody down just a clay shaft that's standing up on its own, but not completely unheard of these days.
Don't do it.
At Hastings, this is a little bit more of a clean-out method than an excavation method, but the contractor there, to clean out loose material on the bottom of the shafts at Pier 5, had a diver go down with a 5-gallon bucket and clean out the bottom of the shafts. That's how they decided to do it. So now we'll look at some tools. Tools can kind of be divided into two categories, rotary and then non-rotary. So here's some pictures of earth augers. Earth augers basically have kind of flat chisel type teeth usually. They might be single flight, so this is an example of a single flight auger. You can see it only has kind of one cutting surface, where this is a double flight auger. It has 2 sets of flights and 2 sets of cutting surfaces. This is our company namesake, Dan Brown, right here, posing next to an auger. Rock augers have more aggressive teeth, generally bullet-shaped carbide teeth. The cutting surface is often kind of tapered or spiraled like this. Here's a picture of one of the rock augers that was used at St. Croix. Digging buckets basically are used, so loose granular materials like sand or gravel don't stay on an auger very well. So you can use a digging bucket. It basically has the similar teeth to an earth auger, but it captures that material in a bucket, and it's got some kind of flap doors on the mouths of that cutting part to trap the material inside the bucket. Clean-out buckets, common tool used on pretty much all drilled shafts constructed with normal rotary methods. Its job is just to get as much loose material off the bottom as possible. It basically opens and closes by turning it, so it has a door that opens and closes when it's twisted. It's not made to cut or anything. It's just made to scrape stuff off the bottom. Now, it's called a clean-out bucket, but if a contractor tells you that a clean-out bucket is fully sufficient to clean the hole, that's generally not the case. So if the contractor tells you that, be wary. Core barrels are basically for cookie cutting through rock. They can be single wall or double wall. They can have a variety of different kind of teeth or cutting wheels on them. The double wall core barrels generally have pipes going between the walls where you can flush drilling fluid through, so it's cleaning the cutting surface, which makes the cutting more efficient. Here's some pictures of core barrels in action at a few of our projects. The project on the left is I-70 Mississippi River Bridge in St. Louis, and the project on the right is back to Hastings Bridge, Pier 5. This is looking at that cutting face of the reverse circulation rig. So you can see it's got cutting wheels that bust up the rock. You can use different types of wheels for different type of rock. And like this hole right here is what circulates the fluid. So that hole is essentially airlifting or vacuuming the cutting surface as this thing goes around. Sometimes we need to scrape the sidewall. This particularly comes into play where you have like degradable shales. So we have tools for that, like an auger with a scraping side cutting tooth, or what we call a back scratcher, which is basically just a cylinder with some wire cables attached to it. So some of the non-rotary tools, chisels. So maybe you've cored some rock, but the rock cores aren't coming up in big solid chunks, so we need to bust them up to be able to get them up on an auger. So you just pick up a chisel and bust up the rock. So this is a chisel that you would pick up just on a crane. This is a type of chisel that you can attach to the Kelly bar. Hammer grab. Like I say, it's often used with oscillator. So you got to have casing with the hammer grab, because if you just went in, it wouldn't hog a very circular hole. But if you need to take material out of a casing, it's an efficient tool for that. For real hard rock drilling, there are percussion drills. They can be cluster drills like this, or single downhole hammers like this. This is a 30-inch drill head from the hammer used at the Highway 53 project up in Virginia. To clean the loose material off the base of the shaft, and also to exchange the drilling fluid and get it clean before we place the concrete, we generally use either an airlift or some kind of a dredge pump. This is an airlift in action on a project down in Louisiana. And here's some other pictures of some hydraulic pumps. So an airlift basically works by, it's just a pipe that we pump compressed air in, and so those bubbles want to float up in that pipe, and those bubbles basically make the fluid in that pipe less dense, or the total density of the material in that pipe weighs a lot less. So just like sucking through a straw in a drink, the material, the fluid around it wants to flow up that pipe. While we're doing that, we need to make sure that we maintain a positive head in our casing. Like I said, that's key at all times. It's easy to turn on an airlift and suck a hole down real fast. Here's some pictures of the airlift at St. Croix. So like we said, they won't, in Minnesota, you're not allowed to discharge straight into the river. So they've got their airlift connected to a hose that discharges into a barge. Once we've got the hole clean, we inspect it. This is some pictures of the mini SID, which we'll talk about in detail later. But it's basically a little diving bell, or a bucket with a camera and a set of lights in it, so we can go down and look at the base of the shaft and make sure it's clean. We also would always use just a weighted tape to feel the bottom. if there's slurry involved and we need to test the slurry, we have tools for that. We have a sampler that basically has a kind of a check valve on it so you can lower it down and it's letting fluid flow through it while you're lowering it down. And then when you start to pull it back up, that check valve closes. So that way we can, if we want to test the slurry from a certain depth, we can lower it down to that depth and then theoretically be pulling a sample from the depth of interest there. And then other tools for checking different properties of the slurry, pH paper, a Marsh funnel test, which basically just gives you an indication of viscosity by timing how fast the slurry flows through a funnel. Mud balance, just like you'd have for testing grout, and a sand content test. Basically, you put a sample in this little glass thing and see how much sediment you end up with, and that tells you an estimate of the sand content. So once we've got the hole cleaned and the slurry clean, time to pick up the cage. We want to make sure that the contractor is not messing up the cage when they pick it. Here's a kind of an extreme example of the right and wrong way to do it. Here's one of the cages at St. Croix being picked, doing it the right way. They've got some internal bracing in the cage to give it extra rigidity when they pick it, and they picked it up with multiple lift points to keep it nice and straight, and then got it in the vertical position. And then they placed the cage. They cut out any of those cross braces that they had in there just for picking the cage. They cut out. We don't want those in there because we need to get our trimming down the middle of the shaft, and we don't want anything that our trimming can get hung up on. The contractor also put centralizers on to make sure that the cage is in the center of the hole. Then it's time to place concrete. As I said, with a dry excavation, it is acceptable to free fall concrete. You just need to make sure that it's not hitting the cage on the way down, which can cause segregation and other problems. Concrete placement in the wet. We want a good continuous pour from the bottom up. Like I say, the theory here is we're going to try to keep as much poor quality concrete and latents and debris on top of that concrete and let it ride to the top. So we establish flow. We want to build a head, and we want to keep our trimmie embedded a minimum of 10 feet. Never, ever pull the trimmie out. That is just asking for trouble. And we'll talk about that in more detail in a little while. Just looking at some pictures of trimmies and pump lines. So generally the trimmie is either supplied with a hopper with something discharging into the hopper, or for smaller trimmies, often you just connect the trimmie straight to a pump line, which is kind of what you see in the bottom pictures here. The picture on the right here is the trimmie at St. Croix. It's kind of hard to see, but this is a pump truck discharging into the hopper here. This is a project on land, so they're able to just back a concrete truck up and pour straight into the trimming. We got to get the concrete to the site, and when I say the site, the place where the drilled shaft is. So when working on water, we're probably going to have a pump in the system somewhere, maybe multiple pumps, or like at St. Croix, they used barges and buckets to get the concrete out to the shaft site, and then they had basically a big hopper feeding into a pump truck that was discharging into the trimming. when we establish the flow of concrete in the trimmie, it's critical that we don't have that first bit of concrete mixing with the fluid in the hole. So we need some method of separating the fluid and the concrete. We can either do that with a plate on the bottom of the trimmie that breaks away when we start placing concrete, or we can use some kind of a pig, which is just a separator that flows down in front of the concrete and separates the concrete from the water. So here's a Nerf ball. This picture is from Hastings. And so, like I said, we're going to have some amount of kind of contaminated concrete that rises up on the top that we've got to get rid of. If you're just out on a ground site, a lot of the time what you'll do is just over pour like this. It doesn't really matter if the concrete goes everywhere, but obviously if you're working out over water, this becomes more difficult. So one thing we can do is use a vac truck to clean away that poor quality concrete. Here's a couple of different scenarios. This is at Pier 5 from Hastings, so this is the trimmie, and this is the pipe from the vac truck. Here's another project where they're trying to finish the shaft off way down in the casing. Another way to do it is basically to pour the concrete higher than you need it and come back later and chip away that poor quality concrete. So at St. Croix, they constructed these shafts and the casings were sticking up, and then they built the coffer cell, dewatered the coffer cell, stripped the casing, and then chipped away the concrete down to where they needed it. So that's what you're seeing here. They're chipping away the poor quality concrete down to the level of the top of shafts.